Thanks for the introduction. So I'm going to talk about performance modeling for computer architecture. I guess previous speakers talk about workflow and network. So together, we kind of cover the HPT space quite well. So a little bit of background about computer architecture modeling and simulation. So it's essential in the computer architecture research and engineering. We need performance modeling when we design, for example, design new CPUs. Also, for example, when we want to do design space exploration to explore different choice. In many cases, we need a performance model. In general, a different modeling approach all have these three goals, which is speed, like how fast it can make a prediction, accuracy, and how accurate is the prediction, and finally, but not least, generalizability. It's how easy to adapt to a new environment, a new architecture. So in this table, we roughly summarize like different modeling and simulation approach and how they trade off between these three different goals. So first of all, we have analytical modeling. They are usually pretty fast because of simplified use of math equation to calculate performance. They usually do trade off between the accuracy and the generalizability. So often more general models such as roofline, which is the previous speaker talked about, is very general, but they are not exactly good for accurate predict performance. On the other hand, you can have more accurate analytical model, but in that case, it's often like tailored to particular application or architecture, which make them not generalizable. Then we have like a discrete event simulator. So for a good simulator, they usually pretty generalizable. You can just change different configurations, and you can simulate many things. But the critical issue of simulators is they are usually very slow. So it's usually impractical to use them to simulate a real-world workload. Then we have emulators such as using RPG. They're kind of somewhere between sacrifice some generalizability compared to simulator, but improves speed a little bit. Finally, recently, people are trying to use machine learning for the modeling and simulation. For each approach, currently, the main problem is they are not very general because the training data is obtained for a particular scenario. So out of that scenario, you will need to obtain new training data and train new models, which is a critical problem of machine learning, previous machine learning-based method. So in this work, we try to explore a new trade-off between these three goals, again, using machine learning. Especially here, we focus on the generalizability, which try to achieve a more general model. And we'll see how we do with speed and accuracy at the end. Our work is called PROREC. So to achieve generalizability, let's go back to the first principle, like what determines the performance. In general, like for any cases, you can roughly say the performance of a computer system is determined by software and hardware together. So a natural thought here, if we want to have a general model, we should be able to separate the performance impact of from software side and hardware side. So in the computer architecture case, I just say the software is a program and hardware is the microarchitecture of processor and memory and stuff. But the problem is it's not very easy to actually achieve such performance separation. That's because in modern computer system, it's the software and hardware have very complex interactions. So it's really hard to like clearly separate them. There's several like previous analytical models trying to do such a separation in a manual way. But again, like they are only like can do it for particular architecture or program. It's not like widely applicable, not general as well. So in this case, instead of trying to manually separate the performance impact of program and the microarchitecture, we're actually trying to use machine learning to learn this separation automatically. So, so that's the main idea of our work. So this is how we separate the performance impact from the program and the microarchitecture perspective. So this framework shows how we do that. So we have 3 models in this case. So on the top, we have yellow part is a program representation model. The input is just a program property itself, and trying to learn a program representation from that. And on the bottom, we have a microarchitecture representation model, which is just using the microarchitecture configuration to learn a microarchitecture representation. So that's our first key idea, which just use 2 separate machine learning models to try to learn capture the performance impact from the program and the microarchitecture. And finally, with these 2 representations, we have the final model to predict the performance when this program running on this microarchitecture. So important property here is like the program representation and the microarchitecture representation we try to learn here should be independent of each other. What it means is once the program representation of a program is constant with regarding to whatever microarchitecture it runs on. So the same program representation should be able to use to predict its performance on when it's running on any microarchitecture, and vice versa. And same microarchitecture representation can be used to predict the performance when any program runs on it. So in this presentation, I'll just mostly focusing on the upper part, which is how to learn a program representation in our case. So first of all, let's see from where we can learn these representations. So the input of the model. So this table lists like 3 general choices we have right now. First of all, it's profiling information, which is commonly used by previous programming models, such as cache misses and stuff like that. So the main problem here is for this information, they usually microarchitecture dependent. And in this case, we're trying to learn a microarchitecture independent representation. So that makes this choice infeasible for us. So the second possible choice is use some static programming information, such as a control flow graph, a data flow graph, etc. So the main problem here is this static information cannot capture the dynamic execution of the program. For example, when you have different input to the same program, it will result in different performance, but this information won't be able to capture that. And finally, we can use the full instruction execution trees try to learn representation from that. And the advantage here is include a lot of details of the execution. So theoretically, it should include all the information that's important for you to make a performance prediction. In this case, we use this instruction execution trees to learn the program representation. But I also bring another challenge here. The main challenge here is a table program will execute at least even more instruction. That's very common. That's a huge amount of information, and there's no existing machine learning model actually can handle such huge amount of information. So to address this challenge, that brings our second key idea, which instead of learning the program representation in a one shot, we kind of like apply a classical divide and conquer strategy here. So instead we try to learn the representation of individual instructions, then try to compose the program representation from the representation of all its executed instructions. So that's our second key contribution. Then we convert this learning program representation problem to a smaller problem to learn the instruction representation. That's how we learn the instruction representation. So for the input of this model, again, like the performance of instruction, first of all, it's of course depends on its own property, like what kind of operation it does and what kind of like memory behavior, access behavior has. But it also depends on other instructions actually running in the processor together. So in modern processor, like that's like a couple of hundred instructions, which is around this instruction. So as a result, we not only use when we try to learn a representation of an instruction, we not only use the property of this single instruction, we also use loads of nearby instruction. Then learn this instruction's representation. Because this is the input of this model is a number of instructions, so it's natural to use just a sequence model here for the instruction representation model. For example, LSTM or transformer, etc. So here we learn the representation of one instruction, and similarly we can, for all the instructions in a trace, we can learn all their representation. Then finally, we can compose the program representation from all these representations. So the details about how to compose the program representation, please refer to the paper. So a natural benefit of having this instruction representation model is naturally generalizable across different programs, because in this case, you can think different programs, they just generate different traces, and different traces just a different combination of the instructions from the same set. For example, assume you compare to the x86 instruction set, and it's just a different combination of x86 instructions. So we can use this single instruction representation model to try to learn the program representation of any program. So next, let's see how do we train this model. So again, go back to the original framework, which kind of simplified on the right. Remember, there was 3 models like in the original framework. In this case, because we replaced the program representation model with the instruction representation model to simplify the problem. So the natural solution of train this model is just to train this entire all of these 3 models end to end. But there's another challenge. The challenge mainly lies in the microarchitecture representation model side. So for the microarchitecture representation model, first of all, the microarchitecture space is highly irregular. It's not as regular as a program you represent using instruction trees. Also, the microarchitecture space is highly it's changeable, and people constantly inventing new microarchitectures. So it's really difficult to really try to train a universal microarchitecture representation model. To solve this problem, let's lead to our third key idea. So instead of trying to train like a universal microarchitecture representation model, we actually do like a random sampling of in the microarchitecture space, trying to just select different microarchitectures. Like so in the figure on the bottom right, we can see like in this case we select K microarchitectures and try to predict the performance on all those K microarchitectures at the same time. So the hypothesis here is if we sample a large number of diverse microarchitecture, and our model can make good prediction on those architecture, we specify they should also be able to generalize to other like microarchitecture, which is not used in the training data. And we will evaluate that hypothesis in the evaluation. So then next I talk about like, how to get the data to train like these models. So in this case, we used Gen5 simulator, which is like a widely used simulator in the architecture community, and we used the instruction simulation execution trace, which is generated from the simulation as our training data. So the benefit here is of using a simulator is we can easily obtain the instruction level latency, which is actually impossible if you want to do it on a real processor. And also, another benefit of using a simulator is it's easy to have many like different microarchitecture configurations sampled. So for the programs to generate the training data, we use a spec 2017 benchmarks and split them for training and testing. And for the microarchitecture to train and test our work, we have like a random configuration generator for Gen5, and we generate a lot of configuration and also split them for training and testing. For the model architecture here, machine learning model, so by default, we were using a two-layer LSTM, and there are more results in the paper about the other machine learning models. So here I show like how our evaluation about the generalizability of our framework. So first, we test the generalizability across for the program that's not used in training here, same programs. So on the x-axis, we have different programs, and for each program, we have like a range bar, which shows the error range across different microarchitectures, and the orange dot there is the average error across all the microarchitectures. We can see like for both seen and unseen programs, the average error here is below 10%. So it can generate pretty well for other programs. So we also evaluate the generalizability across different microarchitectures. So again, it's a similar plot here. So if you compare the left and right plots, there's no significant difference. Actually, the error here is pretty similar. So in general, the result shows our trained model generalized pretty well to both unseen program and microarchitecture. So in the last 5 minutes, I will talk about the use case of our PRORAC work. So how do we use this performance model in a real world scenario? So in this case, we study design space exploration. So in general, you can say this is trying to find the best designs giving objective function. So in this simple case, we're trying to study the impact of L1 and L2 cache sets to a processor. And the objective function we defined here is, first of all, we have active runtime. So again, that's a performance. Then for the second term, you can think it as it's a function of L1 cache and L2 cache. You can think that as a function of area of the die. Again, this is just an example objective function, and any objective function is workable here. So the goal here is trying to find the best L1 and L2 cache sizes giving this objective function. So let's say how to do design space exploration in our case. It's a little different from the traditional design space exploration method. So recall that the microarchitecture representation, which we ignored in the previous slide, but here actually we need to train a microarchitecture representation. So in this case, we just have a very simple two-layer MLP model, which take the L1 and L2 cache sizes as the input, and then trying to predict the microarchitecture representation under those cache sizes. And when we're training this small MLP microarchitecture representation model, the instruction representation model on the top is a freeze, is a pre-trained from the previous data. So for the training data, we just simulate 3 benchmarks here on Gen5, and using those trees to train this small microarchitecture representation model. After this model is trained, we'll be able to use it basically to predict the performance of all these programs under all different cache sizes. So here shows the results of the design space exploration. So the first naive solution here is to use Gen5 to simulate all the combinations of L1 and L2 cache sets. In this case, in this small case, it will take 600 hours. And previously, people had proposed several machine learning-based methods trying to reduce this overhead. So the idea of previous work is based on that they instead of simulate all the combinations, they simulate a part of them and use those partially simulation results to try to train a model and predict the performance on other configurations which they don't simulate. So the challenge for them is mainly to train an accurate enough model, they will need to simulate many configurations for each of the program. So that result in a much larger overhead. And the table on the right actually shows this overhead. So on the table on the right, we compare with several previous work in terms of both overhead, which is how long this design space exploration takes, and the quality, which is how close it to the actually optimal solution. So we can see here, for the previous work, it takes at least 80 hours. But for our project work, it only takes 11 hours because we only need to a very small amount of training data because the instruction representation model pre-trained is generalizable across all these configurations here. And in the meantime, we have a comparable quality compared with previous work. Again, this is like a small design space evaluation. We expect when the design space evaluation become larger, and the performance benefit of ProVac will be even more significant. So in summary, let's go back to the original design goal of performance modeling. For generalizability, we claim we have good generalizability because we learn independent program and character representation, which are reusable across different cases. For accuracy, we also saying we can have good accuracy. The reason here is we're trying to learn the representation from the abundant instruction execution trees, which is have very rich information, and so we can potentially get good accuracy there too. So for speed, once we get the program and the microarchitecture representation, we only need to do a simple combination of them to make a final performance prediction. So we also have a very fast speed. And in the last several minutes, we showcase of how to use it in design space evaluation. We expect there are many other use cases for this framework. And we also open source our code on the GitHub. So feel free to check out if you're interested. Thank you very much.
So yeah, we do have time for a couple of questions.
Thanks for that talk. It was really interesting. What I'm kind of particularly interested in is, obviously you're getting some level of error, and it's not awful, but there's some level of prediction error. Where do you think that stems from?
I'm sorry, some level of what? I didn't get.
Like error.
Okay.
When you're predicting, right? Where do you think that stems from? Is it something that's embedded in your instruction trace? Is it something which can go away if we improve a model? Where does it come from, and what can we do about it?
Yeah, that's a good question, but also like a mystery question. So because performance prediction is essentially from a machine learning model, so it's really hard to tell where is it exactly from. So in general, you can expect maybe like a lot more training data, and maybe probably there's a better models there also. So yeah, they should, in general, they should like improve accuracy. Yeah.
Hi, Brandon Tran, University of Wisconsin-Madison. Thanks for the talk. I was wondering, so most of this traces seem to be on CPU code. Do you anticipate any difficulties of going to GPU code at all?
Yeah, that's a great question. Actually, we are actively working on it. So for GPU code, it's difference here is a more thread level paradigm, but less instruction level paradigm. So it's kind of a different challenge here. So yeah, but I totally agree. It will be also interesting to have having this work for GPU and other stuff.
We have time for one more question.
Thank you for the talk. So is there any interesting findings that you had from running this tool, because you sped up the performance prediction so much? So did you find any unexpected things that the CPU designers are not doing or the program instructions are not doing that could lead to better performance?
I guess that's mostly it's a good question, but I guess it's mostly like future research. So in this case, we're trying to basically build a fast, accurate, and generalizable model, and it can be used in many cases, including explore the things you are interested, like the question you have. Yeah, but we don't especially study those kind of problems in this paper.
Thank you.
So I saw there were more questions in the audience. That's great. Feel free to talk after the session. But for now, let's thank our speaker again. Thank you for the great talk. And with this, we conclude our session. Thank you.